Welcome to the HED, High Energy Density Scientific Instrument. This experimental hutch here is dedicated to research of matter under extreme conditions. We are researching, for example, matter under very, very high density, more than solid density, or extremely high pressures, many millions of the pressure of the atmosphere, which means megabars, or extremely high temperatures of 10,000s, maybe even 100,000 degrees Celsius. You might ask where you find these kind of states of matter. For example, in the Earth core, we have iron and maybe a little bit of nickel under 3 to 4 megabar pressure and very high temperatures of several thousand degrees. If you think about extrasolar planets, those are composed of helium, hydrogen, water, ammonia, but all under extreme conditions of temperature and density. If you think about neutron stars, for example, they have very high magnetic fields. And we can also use our lasers here to simulate very high magnetic fields and study these materials. Now, it is clear that you cannot keep a state of very high temperature, pressure, and density for a long time. It will start to evaporate, it will start to explode, to dissolve. It's even difficult to find materials to keep it squeezed under these kind of conditions. So typically, these states of matter, which we research here, only live for a very, very short time. We call them transient states of matter. They live for picoseconds, femtoseconds even. And this is why you cannot bring them to a synchrotron and expose them for milliseconds or even seconds. But we need to do it here at the X-ray free electron laser, where we have about 50 femtosecond pulses of very hard X-rays here, from 5 kilo electron volt up to 25 kilo electron volt. And we can prepare these kinds of states of matter here. And then within basically 50 femtoseconds, we can apply very advanced X-ray methods to study that kind of state for basically a snapshot, which is shorter than the period of a phonon. How do we prepare extreme states of matter here at HED? Well, we have a variety of drivers, most of them contributed by the HiBev User Consortium. And let me start with something which is on the roof of this experimental hutch. We have two of the most powerful lasers here. One, which is a femtosecond laser with several hundred terawatts, and we can use that to prepare relativistic laser plasmas. The other one is an all diode pumped high repetition rate long pulse laser, which provides up to 50 nanoseconds at 100 joule. And we can use that laser to drive matter by shock compression, by laser ablation shock pressure to several megabars of pressure. These lasers we can bring downstairs here into the experimental hutch, and we can put them into the interaction chamber 1, which you see behind me, which is a multi-purpose interaction chamber. And we can use both of these high-power lasers to create plasmas here. We have then furthermore the interaction chamber 2, which is dedicated to hard X-ray diffraction, precision X-ray diffraction camera. And in this chamber, we can either have the dipole shock compression laser to make shock compression experiments at high pressure, or we can use a diamond Anvil cell station, which is an alternative setup in that chamber, to squeeze material under the tips of two very highly polished diamonds and create also megabar pressures. To change the condition in this experimental diamond Anvil cell station, we can use either a little piezo driver to squeeze the diamonds, or we can use the pulsed laser heating setup to shoot a little pulse of infrared light, heat the material which is squeezed between the diamonds, and therefore, for a very short time, raise the temperature. In order to exploit the unique 4.5 megahertz repetition rate of the European X-FEL to record movies with 220 femtosecond timestamps, we have a detector bench at the end of the experimental hutch, which we can shift all the way from interaction chamber 1 here to the back of the hutch. And it will have an Egypt 1 megapixel detector, which is capable of recording up to 352 images at 4.5 megahertz. Finally, in the next year, we will also install a setup here for pulsed magnetic fields, which is a capacitor bank which can drive a pulse magnetic coil, which exploits for about 1 millisecond up to 60 Tesla magnetic fields, where we can study materials under very high magnetic field influence.